Welcome to an exploration of one of the most significant yet underreported technological revolutions of our time: quantum sensing. Unlike conventional sensors that operate according to classical physics, quantum sensors harness the strange properties of quantum mechanics, superposition, entanglement, and quantum coherence to achieve measurements once thought impossible. Today, we'll journey through the fascinating world where individual atoms can detect magnetic fields billions of times weaker than Earth's, where brain activity can be mapped with unprecedented precision, and where ancient ruins can be explored without moving a grain of soil. This is the story of how quantum sensing is fundamentally changing our relationship with the physical world. At its core, quantum sensing represents a paradigm shift in measurement science. Traditional sensors are fundamentally limited by constraints of classical physics. Signal-to-noise ratios and environmental factors create a ceiling for what can be detected. Quantum sensors, however, operate at the theoretical limits of measurement precision, defined by Heisenberg's uncertainty principle, essentially reaching the fundamental limits imposed by nature itself. Recent breakthroughs at the UK National Quantum Technologies Programme have demonstrated magnetic field detectors with sensitivities approaching 1 femtotesla, that's 10 to the power of minus 15 Tesla, approximately 10 billion times weaker than Earth's magnetic field. This extraordinary sensitivity comes from manipulating individual atoms, typically alkali metals like rubidium, placing them in states where their electrons become exquisitely responsive to the slightest environmental changes. What's truly revolutionary is that these aren't just laboratory curiosities anymore. We're now seeing practical devices that can operate in ambient conditions without requiring extreme cooling or specialized environments. The fundamental principle involves creating and maintaining quantum states that interact with the physical world in predictable ways. When a quantum system encounters an external field or force, its quantum state changes in measurable ways with extraordinary precision. The technology leverages quantum coherence, where particles maintain defined phase relationships, creating interference effects that amplify tiny signals that would otherwise be lost in background noise. Perhaps the most exciting application emerging in 2023 is in the field of medical diagnostics, particularly in brain imaging. Traditional magnetoencephalography, or MEG, requires superconducting sensors cooled to near absolute zero, making the equipment bulky, expensive, and immobile. Quantum sensors are completely changing this paradigm. Researchers at ChewSpin, a Colorado-based company, have developed a quantum-based MEG system that operates at room temperature. This system can detect the minuscule magnetic fields generated by neural activity with unprecedented spatial and temporal resolution. Clinical trials that began this year at Massachusetts General Hospital are exploring how these sensors could revolutionize early detection of neurological conditions, including Alzheimer's disease, epilepsy, and autism spectrum disorders. These quantum sensors can identify subtle brain activity patterns that remain completely invisible to conventional imaging techniques. What makes this particularly valuable is the non-invasive nature of these sensors. Patients can be monitored during natural movement, opening new windows into brain function during everyday activities, something impossible with traditional MEG systems that require patients to remain perfectly still. Neuroscientists are using quantum-enhanced MEG to map neural pathways with millisecond precision, providing insights into how different brain regions communicate during complex cognitive tasks. This research is challenging long-held models of brain function and creating a more nuanced understanding of consciousness, memory formation, and emotional processing. Furthermore, the portability of these new quantum sensors makes them suitable for field deployment in remote areas without sophisticated medical infrastructure. Early prototypes of handheld quantum-based diagnostic tools are being tested in rural clinics, potentially democratizing access to advanced neurological assessment in regions where MRI and traditional MAG technology remain inaccessible due to cost and infrastructure requirements. Another remarkable application gaining significant traction is in archaeology and geological surveying. Traditional methods like ground-penetrating radar have substantial limitations in resolution and depth. Quantum gravimeters, which measure minute variations in gravitational fields, are transforming this field entirely. A joint project between the University of Birmingham and the British Museum recently deployed quantum gravity sensors to investigate a suspected Romano-British settlement in Gloucestershire without breaking ground. The sensors detected previously unknown structures at depths of up to 10 meters, with resolution fine enough to distinguish individual rooms and passages. The technology identified density variations corresponding to artifacts that conventional techniques would have completely missed. This non-destructive approach to archaeology preserves sites while providing unprecedented insight into buried structures. The technology is particularly valuable for sites where excavation is impractical, prohibited, or potentially damaging to fragile remains. The archaeological community has embraced this technology with remarkable enthusiasm. In Egypt's Valley of the Kings, quantum gravity surveys completed in early 2023 identified several anomalies that may represent undiscovered tombs or chambers adjacent to known burial sites. Similarly, researchers are mapping the extensive tunnel systems beneath Teotihuacan in Mexico without disturbing the integrity of this UNESCO World Heritage Site. Beyond identifying structures, quantum sensing technologies are helping archaeologists understand ancient landscapes in their entirety. By measuring subtle variations in subsoil composition, researchers can reconstruct historical waterways, agricultural practices, and settlement patterns that have been obscured by centuries of landscape modification. This holistic view of archaeological sites within their environmental context revolutionizes our understanding of how ancient civilizations interacted with and modified their surroundings. Quantum sensing is also making waves in environmental monitoring and disaster prediction. Traditional methods for tracking groundwater or predicting volcanic activity rely on sparse measurements that often miss critical changes. Quantum gravity sensors can detect subtle mass movements beneath the surface, providing early warning of potential hazards. In Hawaii, the USGS began deploying portable quantum gravimeters in August 2023 to monitor magma movement beneath Mauna Loa. These devices can detect changes in subsurface magma volumes as small as 10,000 cubic meters, roughly equivalent to 4 Olympic swimming pools, from measurements taken at the surface. This represents a 50-fold improvement over previous technologies. Similarly, the ability to precisely map aquifers and monitor extraction rates is transforming water resource management. In drought-affected regions of California, quantum gravity surveys completed last month revealed previously unknown groundwater reserves and provided data for more sustainable management practices. The environmental applications extend to climate science as well. Quantum-enhanced satellites are now being developed to measure minute variations in Earth's gravitational field, allowing scientists to track ice mass loss in polar regions with unprecedented accuracy. These measurements provide crucial data for climate models and sea level rise predictions. The European Space Agency's quantum gravity mission, scheduled for launch in 2025, aims to create the most precise map of Earth's gravitational field ever produced, potentially revolutionizing our understanding of ocean currents, groundwater movement, and mass redistribution within Earth's system. Despite the remarkable progress, quantum sensing technology still faces significant challenges that must be overcome. Current devices require careful calibration and are sensitive to environmental interference that can disrupt their delicate quantum states. The cost remains high, with individual sensors typically priced between $100,000 and $500,000, limiting widespread adoption to specialized applications and well-funded research institutions. However, major government and private sector investments suggest these obstacles will be overcome in the coming years. The U.S. Department of Energy announced in September 2023 a $180 million initiative specifically targeting quantum sensing technologies, while tech giants including Google, Microsoft, and Honeywell have established dedicated quantum sensing divisions with substantial research budgets. As miniaturization progresses and manufacturing scales up, experts predict quantum sensors could become standard components in smartphones and wearable devices within a decade, potentially revolutionizing everything from personal health monitoring to navigation systems that work without GPS signals. The convergence of quantum sensing with artificial intelligence presents particularly fascinating possibilities for the future. Machine learning algorithms are increasingly being deployed to interpret the complex data produced by quantum sensors, identifying patterns and anomalies that might escape human analysts. This symbiotic relationship between quantum physics and computational intelligence may ultimately lead to sensing systems that not only detect phenomena with unprecedented precision, but also interpret and contextualize their findings in real time. As quantum sensors become more integrated with AI systems, we may see entirely new applications emerge that we haven't even conceived of yet. Beyond Earth-based applications, quantum sensing is opening new frontiers in space exploration. Traditional spacecraft navigation relies on radio signals from Earth, introducing delays and inaccuracies for distant missions. Quantum accelerometers and gyroscopes offer autonomous navigation with unprecedented precision. These devices can detect the slightest changes in velocity and orientation without external reference points, potentially allowing spacecraft to navigate the solar system with centimeter-level accuracy. NASA and ESA are already incorporating early quantum navigation systems into mission plans for lunar and Martian exploration. Quantum sensors are also transforming our ability to study distant celestial objects. Quantum-enhanced telescopes can detect gravitational waves with greater sensitivity than ever before, allowing astronomers to observe cosmic events like black hole mergers and neutron-star collisions from billions of light-years away. These observations provide crucial data for testing theories about the fundamental nature of gravity and the evolution of the universe. As quantum sensing technology matures, we may soon deploy networks of quantum-enhanced detectors throughout the solar system, creating a distributed observatory capable of studying cosmic phenomena with unprecedented detail and precision. These networks could potentially answer fundamental questions about dark matter, dark energy, and the earliest moments after the Big Bang. The national security implications of quantum sensing are profound and rapidly evolving. Quantum magnetometers can detect submarines from greater distances by sensing minute disturbances in Earth's magnetic field, potentially changing the dynamics of naval warfare and strategic deterrence. Similarly, quantum gravimeters can identify underground facilities or tunnels that might otherwise remain hidden from satellite surveillance or conventional reconnaissance methods. Major defense contractors and military research organizations worldwide are racing to develop and deploy these technologies, with some systems already moving from research laboratories to field testing. Quantum sensors also offer new capabilities for detecting nuclear materials and chemical weapons. Their extreme sensitivity allows for the identification of radioactive isotopes, or chemical signatures, at concentrations far below what conventional detectors can register. This capability could transform border security and non-proliferation monitoring efforts. Portable quantum devices are being developed that could scan shipping containers or vehicles for illicit materials without requiring physical inspection. However, the same technologies that offer enhanced security also present new challenges. The ability to detect previously undetectable phenomena creates both defensive opportunities and potential vulnerabilities. Military planners and security experts are already developing countermeasures and protocols for operating in an environment where quantum sensing is widespread. This technological evolution represents a significant shift in the security landscape that will require new strategies, doctrines, and international agreements. The economic impact of quantum sensing technologies extends far beyond the immediate applications we've discussed. A new industrial ecosystem is emerging around quantum technologies, creating high-skilled jobs in design, manufacturing, and application development. Market analysts predict the quantum sensing sector alone could grow to over $3 billion annually by 2030, with much larger secondary effects across industries that adopt these technologies. Resource exploration represents one of the most economically significant applications. Quantum gravity sensors can identify mineral deposits, oil reserves, and rare earth elements with greater precision than conventional methods, reducing exploration costs and environmental impact. Mining companies are already using early versions of these technologies to identify promising sites and optimize extraction strategies. The financial sector is also exploring applications in secure communications and fraud detection. Quantum sensors can detect attempts to physically tamper with secure facilities or communications infrastructure, providing an additional layer of security for critical financial systems. As these technologies mature and costs decrease, we're likely to see quantum sensing capabilities integrated into everything, from industrial quality control to consumer electronics. This diffusion of quantum technology throughout the economy could drive productivity improvements across multiple sectors, similar to the economic impacts we've seen from the integration of digital technologies over the past few decades. While many quantum sensing applications remain in specialized fields, we're beginning to see the first examples of how this technology might transform everyday life in the coming decade. Automotive manufacturers are exploring quantum-enhanced navigation systems that can operate without GPS signals, using quantum accelerometers to track vehicle movement with extreme precision. These systems could provide reliable navigation in urban canyons, tunnels, or remote areas where satellite signals are unavailable or unreliable. In healthcare, wearable quantum sensors are being developed that could continuously monitor blood chemistry, neural activity, and other physiological parameters, without requiring blood draws or invasive procedures. Early prototypes can detect magnetic nanoparticles attached to specific biomarkers, potentially allowing for continuous monitoring of conditions like diabetes or early detection of cancer biomarkers. Smart home systems may soon incorporate quantum sensors to monitor air quality, detect gas leaks, or identify structural problems before they become serious. The extreme sensitivity of these devices could allow for the detection of harmful substances at concentrations far below what conventional sensors can register. As manufacturing techniques advance and costs decrease, we may see quantum sensing capabilities become as common in consumer devices as digital cameras or GPS receivers are today. This widespread adoption could fundamentally change how we interact with our environment, providing unprecedented awareness of our surroundings and our own physiological states. The true transformative potential of quantum sensing may be realized through its convergence with artificial intelligence. The vast amounts of data generated by quantum sensors, often detecting phenomena at the limits of measurement precision, create both a challenge and an opportunity. Machine learning algorithms are increasingly being deployed to interpret these complex data streams, identifying patterns and anomalies that would be impossible for human analysts to detect. This symbiotic relationship between quantum physics and computational intelligence is creating entirely new capabilities. In medical diagnostics, AI systems can analyze quantum sensor data from brain activity to identify subtle patterns associated with neurological conditions, potentially allowing for earlier and more accurate diagnosis. In environmental monitoring, machine learning algorithms can process quantum gravity data to predict volcanic eruptions or earthquake activity with greater precision than ever before. As quantum sensors become more widespread and AI systems more sophisticated, we may see the emergence of sensing networks that not only detect previously imperceptible phenomena, but also interpret and contextualize their findings in real time. These systems could potentially identify connections and correlations across different domains, from geological processes to weather patterns to human activity, revealing insights that would remain hidden when examining each area in isolation. This convergence of quantum sensing with artificial intelligence may ultimately lead to a fundamentally new understanding of complex systems, from the human brain to Earth's climate to the cosmos itself. As we stand at the threshold of this quantum sensing revolution, we are witnessing a fundamental shift in humanity's relationship with the physical world. For centuries, our understanding has been limited by what our natural senses and classical instruments could detect. Now, by harnessing the strange and counterintuitive properties of quantum mechanics, we're developing technologies that can measure what was previously immeasurable, from the faintest magnetic fields generated by neural activity to subtle gravitational variations caused by underground structures or magma movements. The implications are profound across every domain of human endeavor. In medicine, quantum sensors are opening new windows into brain function and disease processes. In archaeology, they're revealing hidden chapters of human history without disturbing fragile remains. In environmental science, they're providing crucial data for managing resources and predicting natural disasters. And as these technologies converge with artificial intelligence, we're creating systems that not only detect phenomena with unprecedented precision, but interpret and contextualize their findings in ways that transform raw data into actionable knowledge. While challenges remain in terms of cost, miniaturization, and environmental sensitivity, the trajectory is clear. Within a decade, quantum sensing capabilities may become integrated into everyday devices, democratizing access to measurement precision, once confined to specialized laboratories. As we develop these technologies, we're not just creating more sensitive instruments, we're expanding the boundaries of human perception itself, allowing us to observe and understand our world with greater clarity than ever before. The quantum sensing revolution represents not just a technological advancement, but a fundamental expansion of what it means to see and understand our universe. Thanks for watching. Please like, subscribe, and hit the bell icon for updates. Your feedback is appreciated. We hope to see you again.